Okay, hello everyone, and welcome to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and welcome. Today we will continue making the disassembler, and if you'd like to follow along, please don't hesitate and welcome. So let's go back to the project. I already opened it, and you know, the last thing we did was pretty much we continued to making the we disassemble another instruction, which was the FLD instruction, which is the load a floating point. You know, it's load floating point to ST0 specifically, and that's all we did. You know. So if I run the, let's go and test it here. There you go. We have a float to the address blah, you know, and that's it. You have your resume, PL line XMM0, you know, the other instructions as well that we had already disassembled. And you know, there's still some things to do with these things. The formatting, for example, for example, places where we shouldn't print anything, well, we still do the printing. But yeah, I mean, I think even though of that, we have done a pretty good job for defining a way to solve the problem, you know, and you know, that's pretty much the way to go. So now, the thing I want to try to do is, if you see here, well, I mean, coming up with the formatting and stuff like that, we still have a problem. Well, I'm gonna go to code so I can show you. We still have a problem with the way that operands have to be resolved. You know, right now we just have like this super hacky way to do it, in which we just like, well, right, we just get them and that's all we do. Or well, I mean, for being more precise, we just we don't handle multiple a multiple way to extract those things. You know, for example, when we do a fetch memory operand, we do have the way to go and fetch a register in the operand, you know, like in an address size, you know, which, I mean, this is like the basic bare bones things that we can of expecting there. But some instructions do, let's say, they do have well, be more like to the thing that I was like trying to explain is like the effective operand size here. We resolve it in the we resolve it at first with the effective operand size thing, where we just say, well, you know, if we have an operand address side override, we just modify at the first pass. Then on the effective operand size can also be whenever we get pass onto the we still have the mnemonics, the tables and the entries have ways to override those operand sizes, that effective operand size, which we don't do right now. And you know, I thought it was like a second problem. Well, I mean, we can do that as well. You know, it's something that's also missing. We have to address many stuff as well. You know, the way that we access stuff, the way that we want to like see things going. So I think, I mean, the more and more we add more instructions that have the diversity of the information that we need to construct this assembler, the better we're gonna do it. You know, it's just pretty much like knowledge. You know, we're constructing the knowledge about what the disassembler has to do, making passes on it. You know, we just do one little thing, you know, one instruction, and we just like pretty much inline that stuff, you know, like, oh, this is the thing necessary to disassemble one instruction, and it's like, oh, okay, so now this is the thing that we need to disassemble two instructions, and so on, you know. And right now we disassemble I don't know how many, but let's see, I think 5. 1 2 3, yeah, 5. So we disassemble 5 instructions, so we have a knowledge that encompasses these 5 instructions. So it's pretty much that way that we've been like pushing through this, and it has been really it has been successful, you know. So I mean, I think I always mention this, but I mean the more specific you go in problems of this magnitude, you know, like they have like these intricate specifications, like, oh, this can be like this, or oh, in this specific case it's gonna be this way. Oh, but this now if you have this operand, it's gonna be this way. So this clauses makes you solve the problem being going from a specific to general. And so yeah, so that's the way to go. So let's try to go pretty much and do the same stuff and try to and disassemble another instruction here. Let's see. So we have another example here that we can follow along. This illustrates an opcode with a mother and byte outside the range of 00 through BFH. The structure can be located in section A4. In table A8, the mother and byte C1 indicates row C, column 1, the FADD instruction using ST0, ST1 as operands. Okay. So the 8, let's go to the 8. And we do have well, the mother and byte is, let's see, C1. C1 it's bigger than C0, bigger and equal than C0 and FF. So that means that he has to come on the other side of the table. So it has to be here. So it's C1, so it has to be ST0, ST1, FADD. Alright. So we have an FADD. Okay. I see where this is going. So if you see here, registers are not encoded on instructions the way that for floating point cases, they are not the same. They are not encoded in the way that we will normally do, you know, on general purpose case, you know. For the general purpose, you normally, I mean, the modern table defines that kind of stuff, you know. So if you see here, the modern table doesn't specify a way to access floating point registers. They just have a way to access for general purpose, MMX, and XMM0. For accessing the special registers as floating point, we have to have another way to do that, and that is the way that these tables do it, you know. That basically they just have like, oh, you know, this is it's pretty much implicit on the encoding, you know. That's what that's the solution they gave us. It's like, okay, you know, the table is gonna tell you, well, these are the registers. So pretty much they do all the combinations. So you can see here like S00, 01, 02, 03, 04, 05, 06, 07. And then it's like, oh, FCOM. So if you see here, that's the limit, you know. For FADD, for any kind of well, at least for now. For these instructions, we can just make the comparison, or well, the execute instruction between ST0 and any other instruction in the stack. going from ST0 itself to ST7, and that's all she said. We cannot do fancy stuff like, well, if you think about it, well, there are more registers than 8 registers, so that pretty much fills out the stack. So yeah, if it's a memory operand, probably it should be probably they are these ones, you know. For example, this FADD, you know. If I go and find a FADD on the encoding in this case, I can see FADD, you know, we have yeah, I mean, yeah, for example, I have here all the possibilities in the same way, and this is a little bit more compact because I can see like what's going on, you know, like in this case for 32-bit memory, you know, like single precision floating point in memory, it's gonna come on the mod RAM field, and 64-bit just comes as well, mod RAM field. SDI comes the same way, you know, in the mod RAM, but it's like accessing a register where you have on the mod 11 encoding, and the RM field encodes the SDI register. And the rec field pretty much have well, for memory is 00, so that pretty much explains this one. That's the 00. So this is the memory case, pretty much, and because it has to go, it has to be the 8 within when the mod RAM when the mod base is from 00 to BFH. So you see that? Oh, okay, I got it. That's the whole purpose. That was like, well, why does 00 to BFH? Because if you see here, the other case scenario from C0 to FFH, it's a register, you know? So that, I mean, they didn't tell it, but I mean, that was pretty much stupid, you know? I mean, it was pretty much stupid because they could tell us that, oh yeah, you know, memory registers and memory addressing goes specifically. I mean, they can just tell me that, these little tables here are for memory accessing, and these tables from here are for register accesses, you know, which, I mean, whatever, we find it, but it's it's kind of like, wait a second, so the mod RAM, yeah, we know that from 00 to BF, all of them have to be encodings for encodings for memory, you know, because you have only using the rec and the mod RAM, you have free the mod RAM to access to encode a memory address, you know, a memory operand. But whenever we have bigger values in that, then, you know, we have to access our registers. So registers have a special encodings, you know, with all these combinatorics and stuff like that. Sometimes the combinatory is a little bit different because, you know, you have to solve it a little bit. You have these tables, or you have the addressing bytes and stuff like that. You know, right now we prefixes and prefix overrides and stuff like that. Okay. So pretty much, I mean, that's the same as, what is it? So this is the fetch register operand, and I mean this targets the rec field. You know, this is or the RM now that we got it. So we have a way to access the rec or fetch the mod RAM, you know, and we fetch the mod RAM pretty just the same way. I mean, pretty much this is like fetch. Let me call this fetch RM field. So that's good. We have a way to make the same, which is a pretty simple call. You know, it doesn't have any fancy stuff. Now the thing I was like mentioning is like, well, we could do something like this. I'm thinking about we can make a transformation here where you know, in this place here we access the mod RAM byte and we try to make sense of what it is in the case where we see that we have to go and fetch for the extended opcode, you know, something like that. When we know that we have an extended opcode, we go and try to make sense of it in that place, which I mean it's not bad. I think it's okay. I was just trying to find a way to have a relationship between these two, a more like let's say, I mean, since we're already fetching it, have a more concise way, like, oh, you know, we probably can call fetch register here somehow, you know, have fetch register operand blah blah blah, and we just pass the mod RAM by, you know. And but since this fetch register is more like it's pretty much that, you know, fetch an operand. We are not looking for operands right here. We're looking for opcode extensions and opcode names. So I mean, it's not that too hard to think about a way to do that, but yeah, I mean, I think that's okay. I mean, there's not a problem with that. It's just like the way we constructed it. Like, okay, we have a first pass, we try to make sense of all this stuff, and then we just go pass by and stuff to do the other kind of way, you know. So yeah, I mean, there's not a lot of problem with that. It's just like I think we have to do something with the pointer, you know, because the pointer here is like making the whole thing more complex. So this thing here is it's just like bananas, you know, like we can do better than that. So let's try to do that. So let's see, let me go into here. We're gonna start by pretty much, well, let's add an instruction. It's super simple. It's I was expecting Well, it has operands. That's good. The only thing is that the interesting thing about the instruction is that the operand pass will be pretty much solved on the entry fetcher, which is a little bit which is the case, which is this particular case that we are trying to solve. So that's nice. I mean, that's important. Okay, it's gonna be interesting. So let's add this instruction D8C1 to this string stuff and see what we find out. Alright, so we add that instruction as well. Let's compile what happens. And this is the D8. This is not the same table as we had before, so we have to make some changes now. We have instruction stream, array can, instruction stream, blah 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 blah. Now, the thing that we like trying to mention is like another stuff that we have to try. We can do that, or let's try to do, instead of doing this D8C1, which is, I mean, it's alright, we just know that that encoding is so like that. Let's go with DD, like let me go to DD, because that's one table that we already have. The DD, there you go. But now we're gonna add another entry in there, just because I want to see that resolution in that port. So DD opcode nav with another rand by outside. So let's see, we can make the F store. Probably it's gonna be like this double real, but this works with register, so we can work with that, or the F store. Let's see over the encoding. How is it encoded? Here you go. So we're looking for a F store with that STI, So we are looking for, the implicit register here, for example, is ST0, because since all instructions here work with ST0, well, at least most of the floating point instructions. I don't think all, but most of them. So it works like an implicit one. So we have ST0 and ST1, and we are going to store a real value onto, here is this is the DD, the same DD, and this is the mother RAM, which is bigger than C0. In fact, it's something like C1, ST1, isn't it? Oh, it's the well, it can be anything, D0, D1. Okay, well, I mean, we can do FSD and FUCOM, whatever. This is a little bit better because it has two of them. So I think I'm gonna do FUCOM. FUCOM is an order compare. That means that it's not gonna check for the exception handler, which is, I mean, it's just an example, I guess. And we can just use any kind of example, you know, like it has to be DDE1, you know, so it has to be DDE1. So we use ST1 and ST0. Okay, so let's do that. FUCOM, ST1 and ST0. So we're gonna use that. It's gonna be on the same table. And well, the first thing we like to do, I want to go to the mnemonic thing, try to do the same stuff here we'll be doing before. We know that we have the same case as DD, so we are not gonna make any changes in there. The only thing that we need to do is just like, well, now the case is that the mother and by it's outside, you know, so we're gonna just use the whole mother and by to define the thing, and we just have to find it there, you know, so probably there's not a lot of change in there. You just have to have the encoding correctly. So if we go to encoding, we can go and do that. And we can just say, well, you know, I want to have another entry here, and this entry is gonna be the call. It's a FUCOM, sorry. It's a FUCOM entry. With ST1 and ST0, I can call it like that, I guess, whatever. So we have a FUCOM, ST1 and ST0. These are some state of table entries. Where is it? That's okay. The mother and prison, it is prison. Well, no, in this case it's not, isn't it? Because all the registers are gonna be defined from there. So yeah, it's not gonna be prison. The unfilled prison, in this case it doesn't matter because we're not gonna, well, yeah, well, it doesn't matter because the way we have the code doesn't, it's not gonna enter. But the NF field, well, probably this is true because, well, we can go ahead and look at it. Since we use the whole model RAM, we don't even check for the N and N. It's like if well, I'm gonna keep it that way for now. We don't have an NNM field, you know, because we use the whole thing. So reactive model RAM is gonna be false as well. We don't care about that. We have immediate. We don't have any operand size, so memory operand size. It's, I mean, it's implicit. Let's say we do have an operand size, but we don't have to make the resolution because it's implicit. Okay, so it's just invalid that stuff, you know. The operand count, it has two, you know, we can do that thing. The mnemonic count, the mnemonic name count, string length, this is gonna be another case here. This is FUCOM string, FUCOM. So now that I have that FUCOM stuff, I would like to add it in here. So let's say we have, I don't know, group. This has some state of table groups. This is gonna be the same. Now, which is the DD here? Is the last one. And here by count, of course, it cannot be 1 all the time. We have to have a table that matches this stuff. So I'm thinking of making a struct here, which is gonna be called EagleFly up entry info. I don't know if I already called this, and it's gonna have EagleFly up root type. It's gonna have its type. We're gonna have UNTT or byte, and we're gonna have, how we call, up byte count. You know, this is the thing that I want to use here. I'm gonna keep it right now here, but this is pretty much we're making the spec for what we want from the table. So I want to have this, and we can also have the strings in there. Cute, you know. Now string, I mean the string well, let me first do the compression for the other, and later we're gonna think about how do we want to compress this stuff, which we can do of course, but since it's a little, I mean, we are just seeing like what does instruction need, what do we need, what are the attributes that define each instruction, you know. It's pretty much really arbitrary right now, so there's not too much of a compression right now, you know. It's better to have it this way. So let's see if we can but this we can, you know, we can just start the same way that we had before. So let's say here we're gonna have fly up entry info, which is the mnemonic entry info, yeah, and this is entry infos. These are gonna be how many, 128, whatever, and this is gonna be int32 entry info count. You know, and we're just pretty much gonna do the same stuff here, you know, entry infos. And my bad, because the up by is gonna be independent, you know, the type. We can make the type and the up by count probably. So yeah, because this is more like a huge table and you just like keep adding it. So we can just say something like that. Alright, so if you do it that way, this is calling them mnemonic, but they're more like the group thing, you know. So we have the op table groups, group type, group op by count is gonna be fly up group info group info Now we have this thing group type invalid. Oh, okay, we have the check for the stuff, which we can keep, I guess. Yeah. So, but this will not be well. So we'll need to do this. Just do that, and then we say info for type, blah blah blah. Just keep using it. So we just say info op by count, and first byte of index is gonna be op by index and stuff. Now here's the problem, because since now we're gonna have more than one, this is gonna be, well, no, this is correct, yeah. So now we loop through all the op by counts that this is gonna be needing. Now this is not correct, because we have to move the op by index by every time we have to do it, you know. So it's just like that. something like this, and then now this is op by index. And entry index is the same thing. Now disassemble state op by entries group the first op by index plus index, and well, offset you know, and that's so she said. Now this will get op by index correctly, you know, because we're just gonna well, no, because we start by 1, isn't it? So we have to start by 0. So we just correctly. And entry index is gonna be entry index, which is starts by 0 equally. Now entry index shouldn't be started by 1, because that's what we do, isn't it? We have total entry count thing that we are just pushing, so the index I cannot be indexing to a null one, so yeah, it has to start by 1. So it has to be like that, you know, entry index has to be by 1, and I think that's all. So let's compile, let's resolve this, and this is gonna call fly up group info. There you go. Now this is gonna be fly up group info, and there's no array count group types. It's now group infos. So yeah, something like that. So if you do it that way, then all we need to do is just to pretty much go and do the same stuff in here. So probably that's we can start with that. So C by E1. So we have E1, yeah, that's the mother RAM by, and the first one is 0 0, and now by count is 2. This is E1, so this is correct, we got it. We return the result, we got the entry index, we move pass by, the main by, +1 in this case. Now in this case probably we want to move the whole thing because we're already using it, but since we are not gonna even do that, well, hold on. So let me go to the result. The result is a FUCOM, that's correct. We have 2 operands and the other stuff is just bananas. Just bananas, okay. We just print instruction there, which is a FUCOM, and well, that's interesting because, well, that's the instruction we want, and the by is gonna be incorrect, of course, in here because the by is pointing on to E1, which is the mod RAM. So whenever the case, let's change that. Oh my god, I have air in my stomach. So here we pass by main by. Here we also want to move main by. So that's the simplest way. Of course, it's not like super the best thing to do, because what happens if we didn't get the entry, but we didn't get the entry here either, so we didn't get the entry and we go for an extension here. Of course, yeah, we will be moving the mother and by like crazy, so we have to make sure that doesn't happen, of course. So what we can do is to have this. I'm gonna copy this. I'm gonna put it here. Now, one thing about it, we don't need, since we already have all this stuff, we have main by, and we want to make sure that here we don't pass to main by, because we'll get moving this stuff twice. Well, the way we work with this, I mean, since this is like a special case, yeah, let me go back. You don't need to do that yet. It's just like this special case where we move the main by here. So yeah, let me put the dude here. So yeah, that's another important here thing to do, like how to offset it. I think it's better we're using an offset, but let's just first solve this and then we're gonna think about that. So if we do that, let's see what happens. We should have the same stuff now. The entry is gonna be moved. One case. There you go. So now the main of buy, it's pointing to E1, this which is the mod ram buy, and yeah, the other stuff is the same. We return the one pass by there, because we don't care about it, and the same stuff happens, So now C buy should be correct, because C buy should be pointing to DD, which is correct. DD is the next instruction, and this pretty much is the same. This is an FLD. There you go, we have an 04 FLD. VM resume. The P align, XMM0, XMM1. And the other stuff as well. That's nice. So we haven't finished with the FUCOM because the FUCOM, of course, has to have operands. So let's do that. So let's go with the operand stuff. The operand in this case, which is kind of interesting, is gonna be encoded on the table. So already by here, we already know what operands we are getting into it. So let me see how can we do this. So we can just make the resolution of the entry and either make, we can just keep the same way, like have the same syntax, and just here whenever we do the extraction, we we can start happening to change this a little bit, so it does more of a thing, because if you think about it, well, we can just have something super simple. Let's say we have something like this, I want to get rid of this, we don't care about it. That we can just go like that, and we can just inline that, so we're gonna push that into the places where we need it to. So for example, for fetch memory operand, like I can go there, so let me go fetch memory operand, and the entry is gonna have the whole thing into it. I can say here if entry disassembling state entry while they're in prison, we can do something like that. And here, well, let me go first to the other case. This is okay, it's just I'm just bypassing each case. Fetch register operand, we can do the same here. Well, over here we can just say, well, so for this case, what we're doing right now is you have an end of field prison. So we can pretty much make the resolution now inwards inside this call. First we're gonna make sure that we have a mother RAM, because if we don't have a mother RAM, there's no way to go. So mother RAM prison. Now the mother RAM prison, of course, now we're gonna change the notion of mother RAM. The mother RAM is always gonna be present in this case, because we're gonna go and make the fetching just directly into it. So I would like to pretty much do that thing and say something like, I want to say fly up entry, table entry. It's called a table entry, or would we change it? It's mnemonic entry, isn't it? Mnemonic entry. There you go. So we are kind of compressing and taking the complexity from here, the usage code, back onto the codes that we made, which is good. And in this case we're gonna use something different where we can say that how can I say, because since we already fetch it as a memory operer, we just do a pretty standard way there. So we can say we can use the operand size. Well, we just need some flag. Let's say if we have an extended opcode, we're gonna do fancy stuff with the entry, saying that the operand count we can have this stable, we can have it even here, you know, like, where is it? The same way we have it here, you know, it's just like another case scenario, you know, where we copy this and just have SG 0 Or when we say floating point. We can have it that simply. Of course, it all depends on whether if the instruction is escape opcode or not, but we can do it encoding with that. Okay, why not? So we can just say that we can say, well, instead of happening to find out the rec field just as this, we can have another call here where we do have to do this. I mean, the encoding isn't the rec, I mean, it's still there. The only thing is that yeah, I mean, they have the same weight. ST0, ST1, ST2, ST3, ST4, ST5, ST6, ST7. And whenever we have two, one has to be ST0 and the other has to be ST, another ST, you know, can be ST0 or ST7. Now the order, this is important, the order, how's the order? Let me see. Well, I'm gonna care, I should not care about the order right now. Well, let's not care about the order. Let's just assume that one is ST0 and the other is ST3. So right now we have all that encoding, so we just need the offset to be properly done, you know, so that we have a row and we have I mean, we don't need anything else. This just need a good offset there. So this is a place where we have to change this, because we cannot use this anymore. We'll need to, I mean, it was useful before, because until here, because we had XMM0 and stuff like that. Even, I mean, RAX and stuff like this should be before this one, you know, because since MM0 and RAX are the same stuff, the same stuff well, are the same size, sorry, that was good. But yeah, I mean, we want to have something different here where we say So we're gonna get rid of them. So we're gonna have an offset now. And we don't need any of these anymore because we already have the register. So all this stuff is just gone. Just keep it that way. So let's say we have I don't see any instruction that has more than 2 operands. We can say uh, so wait a second, because yeah, I think I have to read this a little bit more clearly. I mean, just tell me that yeah, it's using 2. Let me go here. So here is ST0, ST0. Oh, and this is the other way around, as you see here. The one is ST0, ST1, this is ST1, ST0. Well, since it's FUCOM, it's not gonna store in a register, you know, because FUCOM doesn't do that. Yeah, FUCOM is this, and it just works with STI. Okay, so I don't see any ordering. Now we know FADD, it stores with ST0, so we can do that first. Let's see. Yeah, here we see the way it's ordered, you know. So probably the order for FUCOM doesn't matter too much, so we can keep it that way. For FADD, we do have a way to do it, you know. We have a source and a dest, you know. This is the way it goes. And then, for example, with this special one, we can keep it on D, you know. We have STI as a source, ST0 as another source, and STD as the destination. In this case, we have, of course, the source and a destination, you know. and the same destination as one of the sources. Oh, okay, yeah. So it's if it's 0, destination is st0. If it's 1, destination is sti. So with FUCOM, there's no destination at all. The destination for FUCOM are the control codes or the condition codes, if that makes sense. So the operands are not going to store anything. Anything is going to be changed at all for that instruction. So yeah, I mean, well, we can just do FUCOM and then let's do FADD. That makes sense. So yeah, I mean, the way they put it, I mean, when they are printed, it doesn't matter, because the reverse order is the one that gives you the idea that they're going to be reversed. So that's good. Well, that's more simple because we don't have to care about that. So we just have to, I mean, we can just follow up the same. Oh, I'm sorry. I'm sorry, I realized that you weren't listening. So what we can do is much simpler than that, because as I saw, it's like they don't care too much about that, because the reverse instruction, it's the one that sets the order on it. So in the way that we see here, we pretty much is the way that we can print it, and the reverse is gonna do the change in a sense, you know. So if we make that syntax for f sub r, for example, which is a reverse subtract, what it's gonna do is, like, we're gonna find st0, st1 in that order. That means that we're gonna subtract from st1 st0, just because of the meaning that we have. So it's just, and that's, I mean, that pretty much makes sense. It just so that the meaning of the reverse is in the instruction mnemonic itself, and not on the operand order, which is, it would be a lot more complex. Just keep the order the same, and that's all. So yeah, so we can just say, well, you know, I'm gonna I was like thinking, well, get register. Well, let's do this one more time. So get register index. Because if you think about it, well, we have the RM rec. Implicit S2SU. Entry index equal let's say we have that for simplicity. Later I'm gonna pretty much do that transformation, but for now I'm gonna work with that. So I'm gonna do that. And then So we can just do the same stuff. I was like thinking, well, why do we add the complexity right now? Later on, if we need it, we can just do it. But first, I want to see what happens, you know. So blah, blah. We're just gonna do the same thing here. I'm just like saying, well, you know, I'm gonna have an index there, you know, where I wanna do that thing. Now, let me remember how did this work. So yeah, I mean, let me destruct all this stuff because, yeah, I mean, this was like garbage. We don't need to do that anymore. We just can say, well, this is good. Yeah, they get register stuff. So we're gonna take rid of this stuff, you know. I prefer to pass it. It's better. Now we'll have like a bunch of registers, even though it's a huge architecture with a lot of registers and memory addresses. I mean, having a table of it is not like too bad. You know, we can do this. So yeah. So we can have the register index already encoded. So the problem is which register I want. I have rec, the mod RAM, and I have the thing. So which one we choose, of course it has to come from here. And I mean, we pretty much can do the same stuff, which we were doing before. So something like that, that's the most simple thing to do. And here we can just say now we can do this inside there if we need to. Well, now I think about it, prefer it that way, so that this doesn't deal with trying to resolve the vector operand size, and it just returns what he needs to return. So it was just the opposite, isn't it? Yeah, because it was counted from backwards thing. So we have to define a fly up register info. Which by now, I mean, it can be, how do we call this? Names entry? So we can do it that way. Now we'll probably collapse this afterwards, but I was just like, well, thinking about it. So register index A. Okay, so now we do that. So let's see what happens now if we try to add something like that. Now I would like to also add in here the by entry count. Here's for now. So we can do it that way, and then we pretty much would like to see what happens now, you know. So let's see. Oh yeah, and the other thing that I was forgetting, the entries now will need to have as well some way to define how it's called, the register A and register B, you know. So so we can just say, well, you know, I'm gonna try to initialize this for FUCOM. We said the mother in prison is false, so we're gonna change that now to true. The VM resume, it doesn't have any mother, well it does because it has the extension. It just gets resolved before. Yeah. Well, yeah, this is false and this is true and this is true and this is false and yeah. So we're gonna have FUCOM entry upper how's it called, register index A equal to blah, register index B equal to blah, and this is gonna be something that we have to find somehow. So we probably have to, I'm gonna go back here. Now I want to do this. Now we have to initialize the table. So probably I'm gonna pass these now. To the up table itself. There we go. And now we're gonna fill it out, you know, names entry, wherever we do the thing. And then over here I want to say that the register index A is gonna be something, you know, which by now, well, it can be st0. This is really simple, probably want something better later, but it was a 10. 0, 1, 2, 3, 4, 5, 6, 9th, and what is the 18 and the 9th. So you know we have to start doing that. Now 1, 2, 3, 4, 5, 6, 7, 9. There you go. So that's the way. And then that's pretty much it. Now I wanna say So let's go and see what happens here. So we get a mnemonic. This shouldn't change at all because we didn't change anything. Just gonna go and do that thing, you know, boom, 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 boom. The entry is FUCOM. That's perfect. Now let's see what happens. Oh my god. So we have a modern percent. There you go, there you go. And we start doing the thing here where we say, well, you know what? Oh, we didn't change this, isn't it? What? The mother and by is the D. No, it's not the D. It's just that we say we move the mother and by, isn't it? We moved it because we were using the by thing. So yeah, okay. So okay, now let's change that. Let's change. Let's change. Where is it? We don't need to do this anymore because now we're gonna go and do something with it, which is, I think, nice, you know, because now we're getting, like, I think we're looking more towards that kind of point. But yeah. So let me go and see what happens now. You know, same stuff. There you go. It should be the same. We have FUCOM instruction. There we go. And the CBY, the thing that I was looking for, is pointing to E1, which is the mother and by. That's perfect because there's the place where we're gonna go. And then we're gonna say, well, you know what, I'm gonna start the extraction, you know, begin open extraction of it, you know, where we go, and then we go and fetch it, the memory operand. There you go. The entry mother and present. There you go. There you go. And then we say, well, the mother and by. The mother and by, this is interesting. Let's see, it's E1, so that means that is yeah, it is that's correct. So the memory operand size, this well, we don't need to do this anymore there, I believe. So let me change that. Because we're already doing it on the other place, so let me change that. So we're gonna fetch the register and parent. Yeah, we do it here. So we don't need to do that anymore. Let's see. Let's go and do this. There you go, there you go, there you go, there you go. There you go. And the effective operand size in this case is going to be 4 because it's the default. So we're gonna go and enter there, boom boom, and then the C entry, it's just the same thing. We could even pass it there, but whatever. Yeah. Oh, well, whatever. Okay. So I think it's better we pass it, but I'm gonna wait there. So mother and present. Let's see what this is telling me about that. Yeah, we have a mother and present. We have an effective operand size validator. Yeah, we do. Now the mother and by it's gonna do blah blah blah, you know, whatever. And then we say, well, you know what, I'm gonna go, we have a register operand size. No, we don't. So we're gonna stay with the effective operand size that we had before, you know, before. Then, you know, I'm gonna get the register index, you know, and just say, well, we got the index from the register index. Now fetch from field is not, so we're gonna get index A, you know, boom. If not index, it's just gonna get it back, you know, because we get it, you know, we get it. We have direct access to it. Just gonna assert that it's on bounds, you know, get the index, gonna fetch for the register. So let's look to the register itself. Huh? Did we say 12? Oh no, it's a. Oh, it's over. Index. What happened there? One more time. Of course, we never set the index. Oh my god. Oh my god. That's the reason. Okay, we have st0. And operand offset. What do we have operand offset? Okay, whatever. So the operand offset is 0 plus 1. Oh, because we think we moved by that. That's a little bit weird. We don't need that anymore. No, fetch register itself. We do the same stuff, you know. Get the mother and by. This is gonna be current of byte what E1, that's correct. Okay, register open size, entry, whatever. Now for this, we're just gonna use the same stuff, and then boom, boom, boom. It's 9 as well. 9. Oh. What? We didn't set it, or what is? Oh, my bad. Yeah, because we passed. Yeah, I mean, hold me a second, because we don't need to do this. Yeah, it was like, well, what the heck? We don't need this anymore. We're just gonna do this by myself. So that's all she said. That's all we needed to do, and that's all we have to do. So let's do it one more time. One more time. One more time. There you go. And there you go. We have 12. There you go. This should be what? DR1. Okay, we are closed. Now it shouldn't be DR1. The index is 12, which is 18. DR1 is, let me see, it's 1 before it, isn't it? So it's 19, probably. Yeah, it's 19. My bad. That was my bad. One more time. So this is ST1, perfect. Now this is ST0, which is correct. Fetch immediate operand. Okay, yeah, that offset thing, I mean, it's correct, but it's a little bit weird where the place it is. So yeah. Print instruction, there you go. Okay, so we have FUCOM ST0, ST1. That's correct. It's not ST1, ST0. Yeah, it's ST1, ST0. Why did you change it? Oh my god. It's because we have direct to mother M, you see? We don't have it, so we could just say that it's encoded in that way. We don't care too much about that. Well, I can change it, so there you go. ST1, ST0, that's the way. It's better. Now let's go to the next instruction. cbyte is now okay, that's correct. We are on DD. Now this instruction should be I don't know which instruction it is. Is the one that we the float. Okay, so the float should be, let's see, also in there, you know, with the main of byte. There you go, we have that. Mother and byte stuff, test byte, mother and byte, whatever. We get the entry index, you know, whatever, and the entry should be FLD, perfect, you know, and same way it goes, you know. So now this entry has the mother and present. It does. I change it now, and because we're gonna get it from the no, yeah, because no, my bad, sorry. So if you think about it, hold a second. Well, hold a second. If I go, yeah, here, well, FGHL. well, whatever, it doesn't matter. I was just thinking like, well, implicitly FLD, what it does basically, it loads the memory operand that we know that this instruction has. It loads it into ST0. So it would be pretty trivial for us just to add that mnemonic just the same way as we were doing before and say, well, we have two operands, one implicitly, but because even better, we can show, since, probably it's not correct because, it's not correct in the assembly way, if you want to assemble the instruction in an assembler, let's say, that would be not the case, but in the disassembly way, which we want to present much more data as we can possibly expose to the user, like implicit registers and stuff like that. That would be really cool. So I don't know, we can choose to do it, we can just choose to expose that information. That's a to-do that I want to see if we can do it as well. But for now, yeah, we just go with this straightforward thing. So let's see. Well, yeah, we're gonna extract it. That's correct. Let's see what's gonna do this in this case now. We got it there, perfectly. Now the C-byte should be pointing to X5. Yeah, that's correct. So we're going to fetch the memory operand. There we go. 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 This is all the same stuff, pretty much the same thing. Oh my god. Now I'm gonna move this upwards. There we go. Now I want to see what happens here. This is very important. Fetch register operand. Now the effective operand size now is gonna be correctly done. So we're gonna do this like the effective operand size is no, so it's gonna be 4. Now we are not gonna need this anymore. We don't have any of the registers there, so we're gonna enter there, do the bananas. We don't need the mother and by whatever. The bits can reverse. The index is 2. That's correct. So we want to do something special for that instruction. I don't know still what we want to do. We do know that we didn't pass anything, so we have the default register operand size. But we know that we just have one instruction, so we could use the register operand size as well, because why not? We haven't think about how do we want to do this in the future, but I mean, right now we just use the operand size that we see correct. For example, the FUCOM, well, it doesn't need register operand sizes, because it has the default. So that's why we have data size invalid there. But since it doesn't have any registers as well, we're gonna just go and look for them, because we're not gonna have anything of this. So we don't pretty much want to do that, or we don't want to do anything with that here, because there's nothing to get, So for one instructions, instructions that just have one operand, So yeah, I mean, I think this is a better way to do it. We're gonna see, if we want to do this, we just want to say that it doesn't stay. Oh my god, it says, oh my god, Disassembling of fetch can here and in here as well. So like we're saying, hey, how many they are, we're just counting them, and if we see an invalid thing here, because hey, it can happen, well, we just say that there's a limit and that's it. So for the immediate, we can do the same thing. No, I don't know if we can count the immediate the same way, because that's why we have, where is it? So you can see mod, how it can. Okay. So we have an 05, the entry is filled, you know, it's correct. We give begin. Now something that I forgot to do, let me just do it. I want to nullify this stuff, cause yeah. So this fetches a memory operand, correct, okay. Now the register operand, we shouldn't get into it, perfect. And then we'll go for the immediate operand, we shouldn't get it anyway, correct. And then operand instruction, okay. We just do the same thing here. There we go, perfect. That's the thing we were expecting there. Now C byte. Now it's pointing on to 0x0f, that's correct. So the entry, it's VM resume, that's correct. Now VM resume doesn't have any operands, so that means that we shouldn't do anything at all. Fetch memory operand. There you go. And then fetch register operand. We don't do anything at all. Fetch immediate operand. We don't do anything at all. And then C byte and operand instruction, the same stuff. Okay, perfect. Now let's continue this. Have a mandatory prefix there. That's right. Now I don't know where C byte is. You can see. Have another OF there. Okay, yeah, we were in 66, but we passed to OF. Okay, and then 3A. This is a PL line. I don't know what happens with this one. The PL line has a model RAM, okay. So we fetch for register inside there, and we just say what's gonna happen with this one. This is gonna register operand size. It's gonna have the overwritten there, overwritten. to the override. Yeah. There you go. We have a null there, so we have to enter in there. So we have an effective operand size. And then we have that this is 1. Okay, so we fetch from the rec, from the RM, sorry. So the offset is gonna be 4, and the index is gonna be whatever, and the register is RAX. So a now this is 8. Because it's size XMMM. No, sorry, 16. Sorry, 16. So 16. It has to be, the index is 5. That's a little bit weird, isn't it? I didn't. Because it should be, well, yeah, that's correct, because so 1, 2, 3, 4, 5. So it's -1, isn't it? Yeah, so that's my bad. Where is it? There you go, XMM0, that's correct. here we do have one. Which is basically the one we passed by, see? Because yeah, what is it? Oh no, we passed 4. Oh, it's because we already passed, but okay. My bad, my bad. We did that, we don't have anything there, so we just say, well, we got there. So we got an offset, and the offset so this is gonna get probably the same values, MMM0. So yeah, this is incorrect. We are missing the width, which is the thing that we forgot about it. So I think this is correct. Now let me see. It's normally false, and whenever we pass it by the fetch here, we pass it with true. That means that we have to get the value from RM and then the value from rec. Now the problem here, of course, is that the offset is not correct, because we have to have the system stay rate names with we have PLM. fetch memory operand. We do that magic. The mother and byte C1. Let me go and see. Yes, it's C1. Okay, perfect. We have an RM and a rec there. We have a fetcher and field, yeah. So there you go. So the offset is 1 times A, blah blah blah. So now we're missing 1. And what about here? The offset should be 0. It's 16. So the offset is what? It's 16, but it was 5. That's totally weird. So yeah, that doesn't make sense. I mean, yeah, that's the reason why I thought it was, because it's the offset, so the offset should be without without subtracting. So let me go back and erase that, because probably yeah, we saw it wrong. Where is it? So now the register is XMM1. This is XMM0. I don't remember. Oh yeah, that's correct. Yeah, perfect. P line, that's correct. Let's go to now this one. The entry is the shell instruction. And let's see what we do. We have an address. We have EAX. We have an immediate. We have an immediate. Oh yeah, because we have to shift by some amount, so we have to shift, because since it's a double, yeah, that's correct. Shift left double immediate by immediate. So that's correct. And then let's continue. I think we have another instruction there, which is another instruction. That's correct. So let's see what happens in here. Address size, there we go. We have an address. Then what we got here, we got something there. And the register is EAX as well. And add EAX block. Okay, I think that's correct. Yeah, we haven't used RAX at all, so that's correct. So we pretty much do that. That's correct. Now this is an invalid entry, I believe. So the other cases are just the same. Alright. So now we have another instruction, which is a FUCOM. And I think that's nice. That's good. So yeah, I mean, we can even try to disassemble the other instruction that we had there before, which was the HC1, which is pretty much the same. You know, it's an FADD instruction. So let's try to do that. I mean, I think it's gonna be fast. So let me see. So we have the 8 and 0x C1, and that's all she say. Alright, so the only problem is that, well, we just need to add into the fetcher over here, another case, which is the 8. And has to be the 8, mothering by blah 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 blah. So I'm going to erase it for now because I know that we are going to add a lot of tables here. So that's all she said, and yeah, so that's all we have to do now. And we get the entry index. Of course, we have to fill the data with that as well, so let's do that as well. Where is it? Over here. Now, yeah, this is rectum mother RAM. Register index A is ST0, ST1. So this is like this. And then it has two operands: data size invalid, memory size invalid. String like this is gonna be mother and byte, and this would go for the mother and byte as well, which is C1. Now, I think I realized a problem now, and is that since we use the mother RAM instead of the we use the mother RAM instead of the main of byte, we're gonna have a problem that right now we'll have a problem because every byte is different. So we have to change that, because either we have to expand in the ID system here where we have a little bit more intuition of what's gonna happen. We have to add the main of byte as well, probably, or do something different that identifies them, because if not, we can find them on another one, and we just pretty much have a bug there where we return a different entry. And that will be just the for now. It's just the case if we have a 1 or 2 byte table, and it's just for the 1-2 byte table and the extension one. Since the extension one uses the other one, is gonna be problematic in there. So yeah, let me put there to do change this is totally bogus. Probably we need an ID system. Opcodes get repeated. Alright. So for now it's not gonna have a problem because all of them are different. So C1, yeah, that's correct, and that's all. So we got the entry, we got that, we initialize it, we say the type, we got the byte and the index. See here, the entry index is just been moving, That's all she said. So that's all we have. I don't know if we need something else there. We can just try to see. So let's run this one more time. Boom, 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 boom. So now we have something like that. We get to the map, blah, 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 blah. There you go. We have a DJ8. There you go. This is outside. Okay, we have a modern buy there. We go for there. You know, I'm just trying to see if we fit it. Now the up buy looks to be C1, and this is zero. That means that he didn't get it. And that's probably because we didn't add it correctly. Let me see. Oh yeah, my bad. This is 5. And that's all she said. There you go. And there you go. The entry has an FADD, and we begin. Now this is gonna go straight forward and just go there. Effective operand size. We got index, you know, which is true, so we have a 9 there. We go and look for it, and the register is ST0, and then just go straight forward and do the same stuff for the other, and push ST1, and then here we don't have anything, so there you go. And operand extraction, print instruction, and yeah, we have an FADD ST0 ST1. It's correct. And let's see till the next one. Now C by it's pointing to DD. It's correct. Let's continue. FUCOM SD1 SD0. Perfect. Perfect. Float. Perfect. There we go. And there you go. There you go. We have another instruction there, just because in the packet we got 2 instructions in 1 packet. So there you go. And probably we have more there, but you know, we just like pretty much are like adding instructions in the simplest way possible. So yeah, we have the resume, p-line, everything looks fine, I guess. The way they are encoded, it looks fine. So that's it. Okay, so please, if you have any questions, post them on Twitter or YouTube, and I'll be able to answer. Yeah. So yeah, I mean, we're getting somewhere. Slowly, but we're getting somewhere. And yeah, I mean, the hardest part is at the beginning, where you have to find out the coding process. But you know, we are getting to the point where like we are finding out that process, and afterwards that, you know, everything is gonna be smooth and soft, you know. So yeah, I think we're doing good here. So yeah, please, what I already said, yeah, post your questions. Please, your questions, make them relative to the theme we discussed on this session. So please, yeah, and I'll be there to answer, of course. I say thank you very much for coming, and I will see you all on the next stream.